is the report on the joint work, which is still in progress with Macrì. In progress because some technical details has to be figured out, but we are confident about that. Maybe not about the length, the amount of time we need to finish, but the idea seems to work. So you will explain motivations and why we can think about semi-orthogonal composition. I will focus on exceptional collection rather, which is a more simple example, not to enter too many technical details, but do we think about this as markings of categories, and then what is the relation with autoequivalences. Okay, so this is all motivated by a result by Macmullen in 2005. But first, you just consider, you just take a P2 and you blow up P2 in endpoints. Then what you want to understand is the automorphism group of X, and especially people interested in algebraic dynamics, they want to find special automorphisms with entropy. We'll define this later, but the main algebraic tool that you can use here is that you easily remark that the Picard lattice, in this case of X, is nothing but the hyperbolic lattice of signature 1. And then you can consider the Y group of generated by the reflections on this. So W is the Y group. So this for this hyperbolic lattice, and there is a old, no, not so old, theorem by Nagata that says that if you have an isomorphism F of such a surface, then this isomorphism is realized at the level of the Picard group by some element of the line. Sorry about that. So there's an element in Wn such that the action of F on the Y group is exactly W, right? On. Okay, so this is a very interesting remark. So when you have an equivalence acting on your, an isomorphism, sorry, go to equivalence just afterwards, acting on your rational surface, then it will act on the Picard lattice as an element of the value. And the question of Macmullen is, can we reverse this construction? Under which condition any element of the value does give an automorphism of your rational surface? So this is the theorem that dates back to 2005, if I remember correctly, that says that, let me state it properly. So if you take, right, that's okay. Thank you. First mistake in my notes. So the point is that if you study this kind of hyperbolic lattices, you, for those who know quickly, that if the lattice is small, then you don't have so much interesting and from a dynamical point of view automorphisms. So the interesting lattices happen for n greater or equal than 10. So this is why we have this constraint. So because the idea of Macmullen is constructing the following thing. So the statement is that for every element now in the Y group of this Picard lattice, there exists a surface Xn which blows up and points P2, and an automorphism Fn of Xn such that the action of Fn on the Picard group is exactly this, given by this element of the Picard group and of the Y group, sorry, and the interesting fact that is interesting for people like Macmullen and other people doing algebraic dynamics is that in this case you can prove that the entropy of such an automorphism, which is just the logarithm of the spectral radius. I will define this in 1 second. Is given, so the spectral radius, if you want, is given by some Salem number. So lambda n is the nth Salem number. And so it's greater than 1, of course. And what's important, so H, so recall that the interesting thing here, this H, the entropy. So if, say, some phi is an action on this hyperbolic lattice, but more in general on some lattice more generally, we don't need this signature in general. So then you can call rho of phi the absolute value of the maximum of the absolute value of the eigenvalues of the action of phi. So you write phi as an integral matrix. We have determinant 1. So in general, this norm or absolute value, because these things, of course, if you want to all the eigenvalues, you have to be in the complex numbers. So, for example, if you take cyclotomic polynomials, you will have root of unity. And the Salem numbers are the first algebraic integers that are beyond, if you want, root of unity. So these are very small polynomials that, or very small degree that the integral coefficient that give you this number. So, but this is something people care about, but they don't care about in this talk. We will not need this, but this is really a great breakthrough for this community and for mathematics in general to have this kind of statement, because it gives you really a recipe to construct such automorphism. While before this result, people were able to construct it by hand with automorphism, and then Macmullen's result is really giving you a recipe that we want to turn into a categorical recipe. So here it produces. So the idea of Macmullen is lifting automorphisms from a cubic curve P, P2, and putting points. So endpoints, say P1, Pn, putting points Pi on C. So already you see this is a special rational surface. So you have to blow up at least 10 points which are not in general position. So this is kind of complementary case to what Johannes Thaler did. You have to blow up 10 points in general position. So
and what is in this example?
F is a very interesting thing, because then you can realize on the level of category as mutations, because what you do is you blow up 3 of the points and you have the Cremona transformation, then you blow up the other points and you move the 3rd exceptional divisor to the end, and then you make a cycle of length n-2 on your points. So if you want, you have your peak of xn, say peak of x10 in this case. So you will have h, which is the pullback of, and then you will have 10 divisors. So let me. So h goes to 3h minus e1 minus e2 minus E3. So this is the Cremona on, so you're moving from P2 to the dual P2 on the Cremona transformation with these 3 points. But then, sorry, 2H, yes, thank you. So this is a canonical divisor. Yeah, sure. And this goes to H minus E1, H minus En. This goes to H minus. So if you did the standard Cremona, you would have this, right? The E minus E1, and this will go to H minus E2 minus E1, right? But then what you do is that you take E1, you replace by En, by E4, sorry, and then you move E10 to E9, and then this goes to, sorry, I'm mixing up things. So this goes to, so E4 goes to, sorry, this goes to E1, exactly, goes to E5 and so on. So it's kind of twist of the Cremona transformation. Right? But here you put E4, you change the, so it's not really the Cremona transformation. You really need to be on this surface in order to define it. And you need a little effort. And then the point that you write down the matrix for this, and the nice thing is that the matrix for this transformation is the matrix for the Lambert polynomial, for the Salem polynomial for this kind of number. Okay, so really a lattice theoretical thing that can be translated this way. And this, if you want to do it on categories, is just mutations. It's an interesting thing because this automorphism of P2 you can see on the exceptional collection that you have on the rational surface. It's just the iteration of some mutations. This is useful for our results.
Where in that construction do you need n greater than equal to n?
This construction, this thing you can do it for every n at least 3. Because it's, otherwise you just have the Cremona. The n greater to 10 is that this result, and I will tell you why, that all the elements of the Weil group are realized. So this is not in general the case. And the fact that you have positive entropy. So you have a spectral radius that is big, because this is simply a very simple argument in algebraic dynamics. You know that Z1 n with n up to 8 is, I don't know what's the terminology, but doesn't have any interesting dynamical property. Then Z19 is tame and Z110 gets wide. So you want your lattice to be big in order to have isometries that have entropy. So this is Macmullen's construction, which is quite a very, very interesting result. And then, why do we care about this? So the first question.
Sorry, I'm very confused about the Macmullen theorem.
Yes.
What if I take W equals the identity? Is that supposed to work with this theorem?
Yes, then you take the identity on Xn.
What's the entropy of the identity?
I
don't understand. Sorry,
and there exists W such that, sorry, you can, sorry, sure, sorry. So I forget that it's not for every W, of course. This is just a simple reflection.
The first part is for any W.
Yeah, sure.
There exists a W.
Yeah, there are two statements. The first is that the whole Weil group gives you an automorphism,
Yes.
which is not the case for n smaller.
Yes.
And the second thing is that since the whole Weil, is kind of corollary, since the whole Weil group gives an isomorphism, you pick this guy. Exactly, this is the Fn that is in the picture, and you know that this guy from some just theory on hyperbolic lattices has this kind of matrix that has this kind of eigenvalues and so on and so forth. And the polynomial is a Salem polynomial, and all these very interesting things in algebraic dynamics I don't understand very well. So, but the first question is, when you discuss with people doing this kind of work, especially on rational surfaces, so you know, Cremona group, for example, this entropy property was used to prove that the Cremona group is not simple, for example, for surfaces. So when you discuss with these people doing another topic in algebraic geometry, they are interested somehow in the same objects from a geometrical point of view, then their question is how to produce. So this is one of the rare theorems that allows to give you a machine that produces entropical automorphisms. So the first question is, can we extend this construction? I mean, the construction is still under the carpet. So I tell you that there is some curve, some cubic, which will be cuspidal. So, and the construction is very, very technical. You need to fix some automorphism of the curve with a very special property, and then you can show that it's liftable. So Macmullen is both a bright idea and a very tough proof. So we try to exploit the bright idea and get along with tough proofs on the categorical side. So can we extend to construction to automorphisms or autoequivalences? Right, so of this rational surface, but why not in general to autoequivalences of category generated by exceptional objects? And even more general to autoequivalence of category in general. So DG category, how do you produce an autoequivalence? First, so the thing we will extend so far is the construction. So the calculation of the entropy is kind of cheating because we know the entropy already. So I will define what the entropy is here. So the fact that the entropy is this is really a specific result that needs a lot of works. We don't have the categorical tool to calculate this yet. But what does it mean extend? So first of all, being able to construct autoequivalences in such a way that the effects that from the theorem that are autoequivalences of this category are a special case. And just let me tell you very, very quickly what's the entropy of an autoequivalence, but then I will not touch this question because it's beyond our game. So if definition, so there is a definition by Mitrov, Haydn, Kazakov, and Konciewicz of entropy of an endofunctor, which is very deep, but we take the definition, the numerical, if you want, definition for entropy. So I take the DG category, or I don't know, triangulated category, or whatever you want. The kind of category, non-commutative scheme, smooth and proper. Okay, whatever you want. So such that the numerical Grothendieck group of D is of finite rank, is free of finite rank. Then if phi is an autoequivalence of D, you can look to the action of phi on this Grothendieck group, and then you can look to, this is a free, so it's a pseudo lattice because you can endow it with a bilinear pairing given by the Euler characteristic, but in general what we care about, I mean, of course it's important to know which kind of quadratic form or bilinear form you want to preserve, but what we care about is really this is a matrix with integral coefficients, and then we can take the same definition as there, so h of phi star is the logarithm of the spectral radius. But I didn't call the spectral radius, so it's rho of phi star. Right? So as I told you, over there I used the hyperbolic lattice notation, but it's really easy. You can do it for every three-abelian group. Right? It's a wild thing, because when you have a linear form or quadratic form to preserve, then you have some algebraic tools to reduce these kind of calculations, but this is the only thing we have. And then the point is that, and this is where this calculation disappears, is the fact that therefore for such x, for such pair x n, so for an Fn, they are constructed by Macmullen in this case, so maybe I could use Fn at some point. The entropy of F, when you think about it as a, so any automorphism gives you an equivalence of the category, is well defined. Well defined because you have two definitions, right? You have this definition by thinking of the action of the numerical growth in the group of the autoequivalence given by the automorphism at the level of categories, and you have that definition that is the one. So here is where entropy disappears. Is something that is motivating our research. Let me make it not disappear yet, because it's also. I mean, the point is that we will not, the focus we have on the generalization of Macmullen is constructing the autoequivalence. So constructing these autoequivalences from the categorical point of view, give a categorical framework to generalize the construction of Macmullen that I will detail later. But the other question is some maybe application to surfaces and exceptional collections. So what is goes under the name of Orlov conjecture. I think Johannes spoke a little bit about this. So there is another result which is due to Cherchanta. In this 2002, I'm not sure about it. And he says that if X is a surface, so any surface, smooth, okay. Everything is smooth and then projected. I mean, it doesn't need to be projected, but smooth. And X is a surface, and if there exists an automorphism of X such that the entropy of this automorphism, so the spectral radius of this action on the entropy is positive, so the spectral radius of this action on the Picard lattice is bigger than 1, then there are two possibilities. X is rational, or the canonical bundle of X is trivial. Okay? So there is this thing which is, you can see, I mean, it's, if you think about it in the general, if the X is of general type, there is no automorphism somehow, so to speak, right? It's very rigid from this point of view. So the cases where we can have this kind of behavior are very special. They must be rational, or, for example, plane-free surfaces. But again, not every rational surface does have such an automorphism. Not every plane-free surface does have such an automorphism. So it's a very special case. But it's related somehow to some birational property, because you can think, of course, not every rational surface does have such an automorphism. But if you think of this automorphism as an element of the Cremona group, then it's related to P2. It's just a irrational automorphism, irrational self-map of P2, right? So here I speak in terms of automorphisms because I want autoequivalences, but you can rephrase all of this in terms of irrational self-morphisms. Okay. So there is a slight generalization of this, which is due to Dominique in 2019, I think. He was a PhD student of mine, so, and then he proved that the same is true if X is not elliptic. I mean, it's not cosine dimension 1. If you're not elliptic in general, then the same is true. So if you have F now as an autoequivalence of dBx with H of F star positive, then you have the same conclusion. X is rational, or Kx is trivial. Right? So this is not evident because, of course, you can have as soon as you have -2 curves, you have spherical objects, and you have a lot of autoequivalences which are not automorphism. And also, if some of you are familiar with the Kontsevich, Zarkov, Dimitrov, and Haydn definition, these kind of autoequivalences have categorical entropy. This is about numerical entropy, which is kind of the rational invariant in this case. So we try to have these kind of results. So I'm trying to extend Macmullen's result to the categorical framework is also thanks to this kind of result. I tell you, maybe this is useful to answer Orlov's conjecture. Does a category generated if a surface has a full exceptional collection? Can we have to blow up to some non-commutative, adding some exceptional objects? Can we find this kind of autoequivalence? Okay, so, but this is something I put as a motivation. I didn't have an answer yet. So as you have understood, if you attended Johannes' talk, this Orlov conjecture is very subtle. So moving from the numerical to the categorical side is a very, very high step. It's not just a little step. You have to be very careful with this kind of construction. Okay, so these are the statements. So the idea is that, for example, another motivation, which is maybe more vague. So this is first question is this one, and the application to surface maybe the second question, and maybe a third question is if I give you a category generated by exceptional objects, but this is still in the first question, can I produce autoequivalences, and then can I play around with lattices? I don't have the hyperbolic lattice anymore, so I will have to develop some technique on other lattices, on pseudo lattices, or these kind of things to understand the entropy of these guys. But one thing at a time. So let me give the definition in the special case of exceptional collection. And then I will give just to make you understand in the special case what we try to do, and then to make a relation with Macmullen's construction just afterwards. So the definition is that if I have a category E, DG, proper, okay, let me be sloppy on the statements, because at the end we will, on the assumptions on the category, we will end up with subcategories, miscible subcategories of derived categories of smooth varieties. So in exceptional marking, of D is a full exceptional collection then you have E1, ER, but I will always use the shortcut E dot. Right, so far you can say, okay, why do you complicate your life? Just adding a definition for something we already know. So far you're right. But when I will tell you the Macmullen's path to the proof, to the construction of this automorphism, you will see that this is really a categorical version of his this idea. So, right, so this is just a definition. Then what I want to consider is the following thing. I take phi from some category D to E. So here all the curly letters, calligraphic letters, are categories with the right property. So I take a spherical functor here. So spherical functors means it has left and right adjoints, and when you make the cone of the co-evaluation and evaluation, you find autoequivalences for the category. And then the definition that we give, but it was already given in the numerical case, for example, we say that it is D-Calabi-Yau if the co-twist of phi, so this is an autoequivalence of E, right, is the self-functor of E twisted by E. Okay, so up to some twist, you get your self-functor as a co-twist for this spherical functor. And the examples are well known. So the two things so far are not related. There are maybe two examples for this kind of CY spherical functor. The first one is if Y in X is an anti-canonical divisor. So everything is smooth, right? So I just don't. X is smooth, Y is smooth. So I take an anti-canonical divisor, then the push forward from Y to X is dimension of X minus 1 CY, spherical. And the second property is that if you take a decanonical double cover, still we can call it still I, right? This is a decanonical double cover. So this is a double cover branched over a decanonical divisor, so over 2k minus 2kx. So I want this divisor to be smooth again. And then again, the push forward is dimension of X, Cy. Okay, these are the main examples that are already in Seidel and Thomas' paper. And what Seidel and Thomas understood is that, and proved for the first thing, is that these kind of functors are nice in some sense, because if you take an exceptional object on X and you push it back, so you take the left adjoint for this one, you get a spherical object. So this motivates the next definition. Now I take a category D, a DG category, right? As your favorite DG category, and a spherical marking. Is nothing but a collection of spherical, an ordered collection of these spherical markings. Is nothing but an ordered collection of these spherical objects. Sorry, the chalk is going to 0, so I don't write very well. Objects. So I have these two definitions and I put them together, and once again at the definition. Now I start with E, comma E, a marked exceptional category. So this is a shortcut to say that I take a category E with the marking giving fixing an exceptional collection. And then I take a phi to be a DCY functor from spherical functor from D to so it is not this is a theorem. So it's an easy lemma or proposition. This is just Seidel and Thomas rephrasing, right? Just an easy calculation. We show that then the collection, if you fix S dot to be the collection by left adjoint of E, is a spherical marking. Right? It's a d-spherical marking. We're just checking that the compatibility of just you use just the triangle defining you the cone here. It's a self-functor, so you're just doubling if you want. Somehow you take, this is nice because somehow you take the matrix for chi, for the Euler pairing for E, and you just copy it on the other side. So it's just a calculation with some shifts. Okay, so it's a very simple calculation. And the definition I wanted to give in the above situation, we say that a d-spherical marking is phi full. So now phi from D to E is D Calabi-Yau spherical. Is phi full if there exists E, a marking of E, such that S is just obtained this way. So if it comes from a full exceptional collection from some category. Okay. And then this is where we mimic Macmullen, and I will tell you in 1 second why, because you have to think. So remember I told you there's a cubic around. I erased it. But you look for the first example. You have a cubic in P2 and one Calabi-Yau functor. And so you have a spherical collection on the cubic and an exceptional collection on your rational surface, and that's it. And this is what Macmullen calls marking. So a choice of an choice of a basis for the Picard group, and the morphism. I mean, I will tell you, but the result we have is the following. We have is the following. So let me define the last thing, and we are done. So talk with all the definitions, but it's some kind of new stuff. So if phi from D to E is dcy, I call hot phi of D. Set then is a group, it is the group of autoequivalences of D, such that for every S full P marking, G of S is a full P marking. So I take a bigger chalk, it's worse and worse. I hope you can read. So these are, what I'm saying is that you pick if you have a spherical collection that comes from a full exceptional collection from E, then you act with G, and you want to find another exceptional collection, the same because the identity is there. And an exceptional collection, a full exceptional collection of E, for which this is the full marking corresponding full marking. Okay, so it's something somehow autoequivalences which are compatible with this back and forth between exceptional and spherical object. Okay? So the theorem that we can prove with Emanuele is that there is a unique group homomorphism of D. So under these assumptions of DCY and E as an exceptional collection of E, such that the following for every G, an autoequivalence is compatible if you want with this spherical functor. The following diagram commutes. So we have E, we have rho of E, we have rho of G. We go to E, we can take phi L, we go to D, we have by G, we go to E, and this diagram commutes. So, okay. So if somehow the autoequivalence is compatible with this restriction, exceptional to spherical, then we lift it. So, first question: is this empty? Is this relevant? What is this guy? What is this thing? So maybe it's just a zero group. Maybe there's no such functor. There's no such object. So maybe we just play around with formalism for nothing, and the answer is so. Example: if n from xn to xn is Macmullen's automorphism, then it is in the image, and then there is a 1CY category D, a functor from D to the D of xn, which is 1CY, and at n is in the image of the row that I just defined. So this is not a fan, but the action of the fan on the category. Well, I have only 15 minutes to tell you why. So I will not speak then about the semiorthogonal decompositions because this is very geometrical. I will explain why Macmullen's construction fits this to motivate our generalization. The generalization is just you replace a full exceptional collection by a semiorthogonal decomposition. You call it marking, not exceptional, just a marking. And then you have a spherical functor, and then you want to lift autoequivalences. There will be some subcategory, not some objects on your category the source category for the spherical functor. And then the automorphisms of D that are compatible with this will lift to the automorphism of E. So you can replace everything, all exceptional collection, full exceptional collection by semi-orthogonal decomposition, spherical object by subcategories. The functor is just a functor. So what's also the point in this theorem is that, I mean, if you think only of objects, you may be surprised, right? Because here you have something, you say, okay, I have a bunch of exceptional spherical objects, say 10 spherical objects. I have 10 exceptional objects, maybe 12, because we want to make balance result. 12 spherical objects on my elliptic curve, 12 exceptional objects on my rational surface, some compatibility between them. So what happens to morphisms? Well, the fact that morphisms go well is that this is a spherical Calabi-Yau. So the point is that if important for the proof before giving you the example. If S is phi full for some phi from D to E, so you have some exceptional collection that is restricted by the adjoint to S. For this CD scale, okay, you have picture upstairs. Then just the fact that you want this to be one Calabi-Yau functor from D to E, from the whole category, not object-wise, tells you that on from Si to Sj equals hom from EI to EJ from every I smaller than J. So RHOM, I mean, the graded ones. So the gluing objects are come with the functor. Okay, so this is the most important thing. Otherwise, I just play on objects. I don't know anything about the category. So this is fundamental. So why this? This is the generalization of Macmullen's result, and why do we call it marking? So what's this? What's Macmullen's idea, and why this is the categorical reflection? And maybe in the last minus 9 seconds, I will give you a couple of non-commutative applications for this, which are so far not very big, but still. Okay, so Macmullen's construction. So if you blow up n points here, so let me drop the n because it's just boring and making things complicated. Blow up of n points. Then, as I told you, there is an isomorphism between the hyperbolic lattice of signature 1n to x. But this isomorphism is when you blow up a lot of time x, even if you blow up 3 times x, you have dp6, you have 2 such maps, so you can choose your isomorphism. So the marking of x is an isomorphism of psi from z1n big X, sending E0, so E0 is the only positive definite guy, to H, so to the putback of the hyperplane section, and the EI to exceptional divisors. So, I mean, this is not, this is already the thing, right? If you have classes that square to -1, then they go to the exceptional divisor. So somehow a marking is a choice. So EI is the ith point blown up. Okay. So maybe the only thing you can want to take care about is don't want minus 2 curves, so you blow up distinct points. Okay. It's quite a standard request. So this you can think of it as a choice of a birational map from X to P2, right? Because the choice of the square one element is the choice of the semi-ample class that gives you the map to P2, right? The divisor pulled back from P2. So then the choice of the exceptional divisor is really telling you which -1 curves you want to build up. So. And what does Macmullen say? So we say that two markings, x phi and x prime, psi, sorry, and x prime phi prime are isomorphic, so isomorphism of marking. If there exists an isomorphism f from x to x prime, so isomorphism between these two surfaces, such that psi prime is obtained just by composing psi. It's an isomorphism compatible with the marking. It's an isomorphism preserving this birational map to P2. Okay, then he defines ot of x psi, given a marking psi on the rational surface x, to be W, to be the elements of the Y group on the Picard lattice Z1n, such that the marking x psi is isomorphic to the marking x W composed with psi. So these are the elements of the Y group which preserve the mark. Okay, and so this is, if you want, these are our this marking is our exceptional mark. It's the choice of an exceptional collection on the derived category, right? So you fix this map. You have a fully faithful functor from P2 to X, which brings back 3 exceptional objects, and then you fix the exceptional divisor. So you fix the other n minus the other n exceptional objects in your derived category of X. So this is really the parallel of the exceptional marking. Okay, for in this case, for this case. I mean, this is an exceptional marking, right? It can be exceptional marking that do not come from the kind of markings. That's sure. This is the reason. This is the sense of the word generalization. Okay, so this is the first thing. And then the other remark is that if you are able to find an elliptic curve X in C, so here we need to blow up points in C. Okay, so this is not a general construction. If you are above, is a elliptic curve. Meaning you see that you realize inside P2, right, as a cubic. So then the points are on the anticanonical divisor. So when you blow up the anticanonical section stays there, even if the anticanonical divisor is no longer ample. Then you can compose. So this is our one Calabi-Yau spherical functor, the special case. Then you can compose your automorphism Z1 and 2x and restrict to the elliptic curve. So this gives a map rho, right? So somehow, if you fix a marking, you can restrict to C. So you see, this is our spherical 2 Calabi-Yau functor. This is our left adjoint to the spherical 2 Calabi-Yau functor, bringing exceptional marking to spherical marking. So what is a marking for an elliptic curve? The marking of C, of an elliptic curve of a cubic C, is a morphism. C is a cubic, which may be and must be at some point singular. Is a morphism Z1n to XC that sends E0 to some ample class, XC, sorry. So some class which embeds C in P2 as a cubic, right? So this is 0, you really want this is 0. And then EY to some degree 1 line bias. So all the other EIs to some degree I line bound with some, of course, you need compatibility or whatever. So, but this is our spherical collection, right? This is a choice of a spherical. So choosing, this is a special case of choosing spherical objects on the which is, in particular, if you want, compatible with the spherical functor. So it's a phi-full, is an I upper star, is I lower star full spherical collection that can be used from these plus the other two exceptional objects that are in the thing. So, out of C rho now, definition, Macmullen definitions, are the isomorphism G of the curve, such that G composes rho is a marking. Same thing, you want automorphism that presents the marking. So that the main theorem, that is, if you want, so the theorem that I told you about, Macmullen's theorem, is exactly the theorem we generalize there, because what does he say? He says that, where did I write it? If C is irreducible, then the marked automorphisms of rho under some compatibility between rho and psi, so if rho is obtained from psi, okay, are a subset. subgroup of the marked automorphism of X. And so there are more here, and this is reasonable because if you don't blow up, if you only have P2, 0, yes, thank you. I thought you say 0 and I was looking for a 0 somewhere. Thank you. For example, if here you have P2, it does nothing, right? But if n is greater or equal than 10, then these two are equal. So every automorphism here is an automorphism here. So we just have the. So our case is a bit weaker in a more general settings, right? We have the generalization of this, which are the automorphism of phi compatible with D, coming from some compatibility with the marking in the Max, with the exceptional collection Max. And then we don't have the inclusion, we just have a morphism of groups. And we don't have the equality, but here Macmullen can prove the equality. And that's it, right? Because now this is the key for this construction of the entropical thing, is that I tell you orally, I arrange the method and I just give one application which is outside of Macmullen results. So we just do not generalize Macmullen just to state again his theorem in a more complicated setting, so we hope. And so what does Macmullen do? And so why we need in our case, I don't find it anymore, the 1CY category is that the curve C that gives you the nice automorphism of X, the entropical automorphism of X, is cuspidal. The point is that if the curve is cuspidal, then the automorphism group is C star acting by multiplication, and then you can easily find easy. I mean, the strategy is to find you take the eigenvalue you want.
So who's doing cuspidal or not?
Cuspidal.
It's
Additive. Yeah, sorry. Yeah. And then you can pick the Salem number as a complex number there as an action on the cuspidal curve. Show that this automorphism is marked. You can lift it, and giving you an automorphism of phi, and then you study the dynamics of this guy, and you can show that this number that acts on the cuspidal curve is an eigenvalue for the action on the surface. Okay, so there is a lot of stuff in dynamics that we don't have any idea of how to do in category, but still, this is the key for Macmullen's result. So maybe just a little application. Very quickly, what can we do? So if we stay here, if we stay with cubics in P2, exceptional collections of P2 and spherical collections, see, the first thing you can think about is non-commutative P2. Non-commutative P2 is what? In our choice is nothing but a spherical marking of a cubic. C is 2, right? Then you have the Calabi-Yau 2 functor, Calabi-Yau 1 functor, and your cubic in P2, but you don't want to take dB of P2 because with S1, S2, S3, sorry, you pick 3 line bundles. Okay. If you know about this. And then what you want is the non-commutative P2 is not this, because these 3 line bundles are not O of 1 and O of 2, but are twisted by some degree 0 line bundles. So you replace P2, you replace this by some exceptional collection, which has a PL of EI equal to SI. So this, you can think of this as definition of a non-commutative. We do have to know how to choose well these bundles. And the point is that numerically this is exactly the same thing. So our hope was we use special curves, we blow up points. So blowing up non-commutative is just picking a point here and adding the spherical object here and adding the exceptional object here. So it's compatible with our construction. So we can blow up, add a spherical point. The degree is degree 1 line bundle S4. Well, not only one, degree 1 line bundle S4 to Sn. And then you will add phi from DBC to the blow up of the NCP2 such that this is generated by n exceptional objects with the property that you bring back this to the spherical object. Okay? So again, somehow the blowing up is just choose one more point on the curve and add it as an exceptional object to the category. So at the end, so the question is, can we find entropical, can we just mimic, take the same automorphism for C and bring it back to the non-commutative 2? The answer is no. So the point is that there exists some NC DP6. So if here you blow up only 3 points, you have an NC DP6 with the Cremona transformation. But there is no NC so there is no blow up of NCP2, non-commutative blow up of NCP2, such that Macmullen's construction, Macmullen automorphism from the curve is. And this is due simply to the compatibility between these three spherical objects. Somehow when you twist your non-commutative P2 is, you don't take O1 or 2 in C, but you twist by some degree 0 element in the Picard group, and this makes things rigid. So this construction by Macmullen, we can show that works only in the commutative case. So it's a very special case. But still, if you only blow up 3 points and you look what does the Cremona transformation do to your exceptional objects, then you can find some conditions which are non-trivial, but still not completely. You have non-commutative P2 that can where the Cremona transformation works. We don't know what does it mean from a geometrical point of view, but this is the first example. Then we are working out another example on exceptional collection on general surface of general type, but already out of time, and then sorry about that.